and that is plane flying downward toward a runway at 149 miles per hour makes an angle of 6 degrees with the runway. Write the vector. So let me write it in a little bigger words for you. So number 18, plane flies downward at 6 degree angle at 149 miles per hour, and they want me to turn that into a vector. So I think a picture would be helpful first off. So here's the runway. Here's the plane coming in, and this angle the plane's making is 6 degrees, huh? And it's coming in at 149 miles an hour. Like that. So it's coming in at 149 miles an hour. It's at an angle of 6 degrees. And how do we make that a vector? How do we make that a vector? And this is actually a little tricky. So the main thing I want to help you with and make really clear is that we're going to start today, especially, going to make a lot of vectors out of angle things. And remember how we started to do that? Didn't I give you a formula last time? Didn't I say a vector will equal, any vector v will equal the magnitude of v times the cosine of theta I plus the magnitude of the vector times the sine of theta j. Didn't I give that to you? Okay, yeah, so that's the main one. We'll just keep using that again and again and again. But the trick, here's the trick with that. Theta must be, that theta in that formula, must be the direction angle from 0 degrees. It must be from 0 degrees. Do you know what I mean? Like, for example, if you have, you think, well, I'm over here, and I have this, 30-degree angle that way, so I'll use 30 degrees. Well, actually, you would have to use the angle from here, from 0, which would be, what is that, 90, and 6 would be 150? It's almost 180, yeah. Makes sense what I'm saying? So whenever you have a vector and you're going to use this formula, you have the angle that you use in the cosine of the angle, sine of the angle piece, that has to be the angle from 0 degrees, what we call the direction angle. The angle from 0 degrees. So what they're going to try to do is trick you by giving you, I don't know if they're trying to trick you, but just real life problems. You just have angles in different directions. So they might have, like I said, here's a good example. They might have an angle, they'll tell you, somebody's pulling a wagon or somebody's pushing a force up a hill. That's what we're going to do in the next section. Or a plane, and we have a plane, or the football, or whatever. You have different things happening, physics basically. And they say it's going that way 30 degrees, Well, we can't use, if you take that 30 and use it, it'll mess you up. It won't work. You have to turn it into the direction angle, meaning the angle from 0. So you always have to figure out how far is the angle from 0. So that would be 150. We would use 150. Does that make sense? So like if they told me it's going 100 miles an hour left at 30 degrees. So if I wanted to turn it into a vector, meaning an ij, this is an ij vector. And I means how far right. Remember, I is the sideways. It's like x and y, huh? The I is the sideways, the j is up, down. Just all of a sudden we're using I and j instead of x and y. I'm not sure exactly why. That's just the notation that kind of caught on over time. So the x is sideways, and the y is up and down. So anyway, if you want to make it that, you'd have to go 100. You don't need to write this down. I'm just making up a little example, but we'll do the real one in a second. You would have to go 100 cosine of, 150. That'd be the I, plus 100 sine of 150j. That's how you'd have to do that. And then that would work, and you'd have your right vector, and it'd all be good. Does that make sense on that? That way the signs will come out right, and everything will come out right if you use the direction angle, meaning the angle from 0 degrees. That's the main lesson. Just always use this formula. Makes sense that cosine is the sideways, because remember, cosine's always x. So sideways, right? We're going to keep using this even into the next chapter. So this is going to be your best friend, basically, in the rest of the course. We'll use a lot of this, and it'll be kind of the same thing over and over again. It can get really easy. Problems that look pretty hard can be made pretty easy if you just always remember cosine is sideways, like we've been talking all semester, huh? And sine is up and down, so it makes sense cosine is with the I, and the sine is with the J, and just make sure that angle's a direction angle, and you're all good. Okay, so let's do this particular problem now. So this one is particularly tricky. It's a good example to show what I'm talking about. We might look at that picture and go, okay, the angle's 6 degrees. It's actually not. That's not going to be the, even though that angle's 6 degrees, but that's not our direction angle. Now, why not? Well, because if this is the plane, P for plane. There's the plane. We'll do a little physics here. And it's coming down towards the runway at 6 degrees. That's not its angle from 0, is it? Well, how do we know? Well, draw 0. What's 0? Straight to the right, huh? Isn't that 0 degrees? Right? You with me on that? 0 degrees is straight to the right, right? On the axis system, isn't this 0 right there? So whenever we talk about 0 degrees, we mean, positive x-axis, straight to the right. Okay, so that's 0. The plane, then, is actually coming in some angle below 0, isn't it? Makes sense, huh? If you're coming down, you're coming a negative angle, aren't you? So how much is that negative angle? Is it 6 degrees?
Would it be the same because it's like a triangle?
Sorta, huh? Yeah. You're actually right. It's not a triangle. You guys remember geometry? Did you have a good geometry experience? Yeah, me either. My geometry teacher was terrible. I had a great algebra teacher. Probably part of why I became a teacher. I had an excellent algebra teacher. He was super serious. I mean, you think I'm serious about math. He was serious. He was out of the Navy and his Navy buzz cut, and Mr. Allison, and every day you came to class, he was the calc teacher on my campus, and and he had all the homework written on the board already when you came in the door. Anyway, he's fun. He's good. He was highly committed. But my geometry teacher was just a goofball. He would just come to class, go up on the board and kind of fool around for 5 minutes, and then sit down at his desk and go read the book, We're like, I can't read the book. Anyway, so I didn't learn anything in geometry. So anyway, though, all you need to know here is alternate interior angles, meaning Z, right? Z is totally right. This is 6 degrees. Here, we're going to need to say negative, though. Negative 6 degrees, because those are alternate interior angles. What do I mean alternate interior? They're Z angles. That's how whenever I teach a little bit of geometry in some of the other classes, I just say it's like a Z. Do you see the Z there? If I draw it that way? See how they kind of make a Z, like Zorro, make a little Z thing there? Right? Those are called alternate interior. The two angles the Z makes, either way, you can do the Z forward or backward. I know I'm doing a backwards one. The plane diagram happens to be a backwards Z. Forwards or backwards, the two angles that a Z makes, they're always equal. And then they look equal, don't they? Don't they look like they are? They are. They're called alternate interior angles, meaning if the top and the bottom are parallel lines, they have to be parallel. And they are in this case, what? Because this is the ground, and this I just did straight to the right because that's what 0 is. So they're both straight, aren't they? They're parallel. So if the top and the bottom of a Z are parallel, then the Z angles, which are technically called, I'm not going to quiz you, you don't need to write it down. Alternate, this is the only problem where we're even going to have this anyway, so it's not something you got to get really used to. Alternate interior angles, they are always equal. These two, this angle here, this opening will match that opening every time. So that means if this little one, I can move it over here if it's confusing sitting there, it's 6 degrees right there. That's going to match this. But this one's negative 6 because it's below 0. So we just got to use negatives. Long story short, we just got to use negative 6 degrees, and it'll all be good. Does that make sense? So, and like I said, they're not going to give you a lot of these. This is like the only one where you got to think about alternate interior. So negative 6 degrees, so with 149 miles per hour. So let's do that. Let me see if I have room here. Maybe I'll just erase the original problem here. So put it up here. All right, so the vector then. The vector will be the magnitude. Remember, the double bar thing is the magnitude, meaning the length or the number. What was it? It was 149, right? 149. 149. Cosine of the angle. Now, what's the angle? Negative 6. And that That will be different than positive 6. Well, not for cosine, I don't know if you remember, but for sine it will. I plus 149 sine a minus 6j. And then we just use our calculator. Just hit the buttons from there. Just want a decimal. So let's crank that out. So that's 149 cosine. Make sure you're in degree mode. I'm getting 148.18 I. Bless you. Minus. It comes out 15.57 J. No problem. All right, good. Is it all good there?
Wasn't it 47? 47?
Did I mess up? 5747? Yeah, it goes on and on.
No, isn't it 1?
No, the first one?
1.47?
I don't think so. Did I get this?
I got it wrong, sorry.
Oh, you little button wrong.
Yeah.
We good there? Let me double check. That is the right answer. Good. Basically, you know why that first one could be negative or positive, because they didn't say if the plane's going that way or that way. They didn't say if the plane is. I made the plane going to the right and down. The plane could have been going left and down. Yeah. In fact, let me make sure these answers are real, because especially if you're headed like to physics, you want to make sure this is real for yourself. So what does this 148.18 I thing mean in the real world? Well, remember, I is sideways. That means, when that plane is flying down here. Let me draw a better picture and be real clear about reality here. When that plane is flying down at 149 miles per hour, down at 6 degrees, that means it's actually going sideways, this number, 148.1 miles per hour, and downwards, straight down, it actually has a downward velocity of 15.57. That's the J. Does that make sense? That's how fast it's coming down and how fast it's going sideways. That's what we've done. Get that idea? Does that make sense? That's exactly, if you're going to go to physics, that's exactly what you do to figure things out, is you just break it into components.
Yeah.
That good? On that? My daughter and I do that all the time. She's taking physics right now, like on so many of the problems, and we'll get to some point, and then she'll say, oh, do I just break it into components now? And I'm like, yep, just break it into the side components and figure it out from there. Make sense? That's what we're doing with IJ. Does that make sense? So you'll have like some kind of diagonal movement, and the I and J breaks it into how much sideways movement that is and how much up, down. It's called the components of the movement, the sideways, right? So like if I, and the same thing with forces in physics. I'm a wannabe physics teacher. If you push up at a diagonal on that door, that really means I have a sideways push, and I have the door is experiencing an upward push and a sideways push when I push diagonally, right? So that's the kind of thing we're talking about. That's what's happening in the plane. As the plane comes down diagonally, that means it has a sideways speed and a vertical speed, both. And you use that in physics to figure things out. All right. I'm not a wannabe chemistry. Chemistry confused me.
Yeah, tell me
But
about it.
physics was very hard too. I mean, but a little more mathematical would probably fit for me better. So length of a shadow, V for the figure is absolute value. The magnitude and direction are given. Write V in terms of I and J, then find the length of the shadow. So what they're saying is, okay, you got this vector V, maybe it's an airplane coming down or whatever, and they're saying, hey, what's its shadow doing? See the shadow down here? This is the shadow. You can see it in the diagram. That's the shadow. So they're saying the magnitude and direction of V, the vector V, right? Magnitude 1.7. I don't know what it is in the real world, miles per hour or whatever. Or inches. There it is. It's inches. That's how long vector V is. And the angle is 32 degrees. What is that angle? That's the... what is that angle?
It's the downward motion, isn't it?
Yeah, I guess that's the actual direction angle. There it is. So that's the one we need. We don't have to adjust it anyway. It is the direction angle. So it's a 32 degree direction angle. And so how do you use that to find the length of the shadow? That's their question. Find the length of the shadow. So very practical thing. Well, they do in real world physics. They engineering. They need things like this. So how do we do that?
Wouldn't you plug it into the same formula and then just take the sideways force?
Excellent, Kevin. It's just, yeah, Kevin's right on the money. It's just the I component, huh? It's just the sideways. Does that make sense? The length of the shadow just is the sideways of the vector, isn't it? Do you see that? Do you feel that? So again, what we're doing with this IJ formula is we're breaking any diagonal thing into sideways component and vertical component, I and J. Well, a shadow is just flat because the ground is flat, right? The shadow on the ground, right? Like look at my shadow, your shadow, look at your own shadow on the table if you put your hand out. You know, how long, if you put your hand out above those lights and you look at the shadow on the table, the length of it is just the sideways, right? If I put my hand diagonally like this, my arm, diagonally like this, then I have a sideways length and I have a vertical length. Well, the shadow on the ground, since the table's flat, is just the sideways length. It's just the I component, isn't it? So basically, they're just saying, just find the I component. So remember what the formula is. It's magnitude of V cosine theta I plus the other one, but that's all I need. I just need magnitude of V cosine theta. That'll be the length of the shadow because that's the length of the sideways component. So it's just 1.7 cosine 32 degrees. Let's see what we get. I'm getting 1.44. How many places? 10th. So just 1.4. 1.4. Oh, wait. First they want the whole vector? Wait, why are they asking for V? Oh, yeah, write V and then file. Okay, I actually just did part 2. Sorry. Let's go back and do. So they want the whole vector in part 1, I guess. Now I'm seeing. So they want the whole vector. So I got to do the other part too. Sine theta j. So they want the other part. So we got to do the whole thing at first.
You would still have the 1.4i though, right?
It's still going to be 1.7. Yeah, right. The other one's to be sine 32j. And so 0.7 sine 32. I'm getting, so it's going to be, so it's 1.4i, and I got 0.9. Did y'all get 0.9? J. And so then the length of the shadow is just the 1.4. Like that. Let me double check. Yeah, we good on that? That makes sense? Questions on that one? So a shadow is a horizontal component. Good. Can I flash off that? And so they want me to draw it and find the magnitude and all that stuff. Okay. Yeah. So what we do is we take a look at it. Like that. And we start from the origin. Remember that? And we got like north up here, south, east, and west. So we're going to go south, 75 east. Remember how that works? That means straight south, but not straight south. 75 to the east of south. That's almost all the way there. So it'd be like that. So that's a length of 100. So this angle here is 75 because it's south, 75 east, huh? So that one's a length of 100. And then, or here, let me put the 100 at the end there. And then the other one, this one, is north but 52 east, so it's like that, but not quite as long. And so and this is 52. That's a 5 there. So north, but 52 to the east, huh? So, okay, so there's the two vectors. This is the 81. So, okay, so what do we have to do? So again, going with that first thing I said, you have to get the direction angles, meaning from 0. Don't you? Neither of those angles are from 0. From 0, meaning like 0 right here. You have to get from 0 and from 0. You tracking with me? So whenever we turn these things into vectors, we have to get the direction angles, which means the angles from 0. And then we'll just use the formula for both of them. You know, the cosine of theta with I and sine theta with j for both of them. All right. So let's do that. What's this angle up here? How are we going to find that angle? 90 minus 52, huh? Because it's 90 all the way, take away the 52. 38 degrees. So that one's 38, good. How about the other one?
15.
Yeah, well, negative though, right? And that matters. That does matter. Or 345, right? You can use either one of those, and it'll work. It'll work well. Yeah. So So this is So you can either say it's minus 15 or 345, but not 15 itself, because 15 itself would be up here positive, huh? That'd be a little bit different direction. You with me on that? So because this it's like two ropes or something pulling on a point. My daughter and I are doing a bunch of those in her physics class right now. So like if you had a rope here and a rope there, and they're pulling, so this one's pulling down at 15, this one's pulling up at 38, and what's the overall force is going to do? So so either one, you can use negative 15 or 345. It'll work. Those are both the same direction, aren't they? We good on that? Well, how about we just use negative 15? I think I used 345 last time. Whatever, it'll work the same. Negative 15. Everybody see how I'm getting that? Because 90 minus 75 is 15, but it is negative. That is important. Okay, so now how do we write the two vectors? We say the 100 one. So this guy right here is going to be 100 cosine of what? Negative 15 I plus 100. Get this out of the way here. 100 sine of negative 15j. Not good? And then the purple one here, that one's going to be 80. Again, cosine comes first, goes with the I. Cosine of, 38? 38 degrees I plus 80 sine 30 degrees j. So let's use a calculator, get the decimals on those. Those are the two vectors. And once we get the numbers, we just need to add those vectors up, meaning add the I with the I and the J with the J. And we got it. That's how you sum forces in physics. It's exactly what you do. So, okay. So I'm getting, and I don't know, I'm still in the middle of the problem, so I'm going to use a couple places of accuracy. 96.59I. Minus 25.88J. The other one, 80 cosine 38. I'm getting 63.04I, and this one's just nice clean 40J. We getting those okay? Getting those two vectors?
Did you put in 30 or 38?
Oh, I put in 30. Why did I do that? Thank you, Kevin. Catching my crazy mistakes. Yeah, I don't know why I did that. Just being crazy. So that's going to change that, huh? So that should be 80 sine 38. So I'm getting now 49.25 J. You guys getting those okay? I, J, I, J.
Then you just combine
And then you just add the I with the I and the J with the J to get the what's called the resultant, the result of those two forces. So the resultant R is going to be adding up the two vectors, so it'll be 96.59 plus 63.04 I plus negative 25.88 plus 49.25 J. So use your calculator there. I'm getting 159.63I. 23.37J. So there's the resultant force. How are we doing? You guys getting those numbers okay? Let me try to help you dial in with what that really means. So one of the ropes is pulling up to the right at 80 pounds. The other's pulling down to the right at 100 pounds. What's the result of those two? There's a right, I is right, There's a right pull of 159 pounds, and there's a, what is the J? Up or down? Positive. So up. So the net, because one's pulling up and right, one's pulling down and right. So, but it turns out the up is going to have a bigger effect because the result is up with 23 pounds. See, they kind of cancel each other out, right? But in the end, it's more up than down. Why? Because the 80 is lower, but it's at a higher angle, So it has a bigger upward effect. So in the end, this object is being pulled to the right with 159 pounds and up with 23 pounds of force. That's what's acting on that object. Is that all they want? The magnitude of the resultant force. So they want the results. So in the end, then, they want the magnitude of R. Like how much total force is being put on that object. How do we figure out magnitude of a vector? Pythagorean. Square root of a squared plus b squared. Remember that? Square root of. They're basically because the resultant force, if you think about it, here's the object again, this result is mostly right and a little bit up. So the resultant force is like that. So that's the result of those two ropes. In the end, altogether, it's like one big rope pulling up to the right. Does that make sense? Those two ropes, one pulling up right, one pulling down right. In the end, you could put them all together into one big rope pulling up to the right, 159I, 23J. That's basically what result means. That's the net effect of them. And so that has to find his length, you just take the I component, and it's like Pythagorean theorem with I and J instead of X and Y or A and B. Same thing. See how we're going to just start using those all the same? X, Y, A, B, I, J, whatever. It's all the same stuff, right? Square root of a squared plus b squared, or I squared plus j squared, whatever you want to call it, sideways and up, down, So it's going to be, right, because that's the length of that, just Pythagorean theorem, little right triangle, right? Whenever we break and this is what we're going to always do with vectors, we break a vector into sideways and up and down, we're making a right triangle, aren't we? So all that we've learned about right triangles is true for this situation, therefore. So 1.59.63 squared plus 23.37 squared, the square root of it, and whatever that is, plus you guys getting it? You use your answer. I use my answer button a lot. It's helpful. I'm getting 161.33. So that means total force, 161.33 pounds of total force. So those two ropes, in the end, are pulling with a total force of 161.33 pounds up to the right. And what angle? What angle are they? That's the other thing they want. They want the angle. What angle right here, theta, is the result? The two ropes, the overall result of the two ropes is up to the right at what angle? How do we find the angle?
Is it just the difference between the two direction angles?
No. If they were equal forces, it would be. But remember, one's 80 pounds, one's 100 pounds. So one's going to have a bigger effect on the whole thing. You can't just do it that way. Remember, we learned it earlier, last time, inverse tangent. Remember, because tangent of the angle is j over I, Remember that? Remember, what have we always learned tangent is? Sine over cosine. Watch all these connections. They all are saying the same thing. Yeah. We've learned it's opposite over adjacent. It's sine over cosine. And what is sine? Y over x or j over I. So those are all the same thing. the vertical over the sideways, huh? So theta then will be inverse tangent, right? So over here, let me do it slower. So tangent of the angle theta is always going to be the j over the I, right? Opposite over adjacent, j over I, or sine over cosine, y over x. It's all the same stuff, just said in different letters and different ways. So theta is inverse tangent of j over I. So that's going to be inverse tangent of j over I. So the j is the 23.37 over the I, 159.63. Tangent is 23.37 divided by 159.63. And so theta equals 8.33 degrees. 8.33 degrees there. So that's the angle of the resultant force.
We don't have to use like inverse tangent all the time. I mean, since we know all the angles, we can use like inverse, like sine or cosine.
Yes, you're right. You could. I'm going to always use tangent because to use sine or cosine, you have to use the r, right? And the r is another rounded number. So, but of course we have it. You could do it. You totally could. Yeah, I'm just going to always use tangent because it's always with the two we've already got. But you can do other ones. Yeah, you're totally right. Good on that? All well? That's a long problem, huh? By two tugboats towing a ship, 160 kilograms north, 40 west. I'm going to write all that down for you. Find the magnitude, direction, angle, same thing. It's exactly the same. So let me write it down and we'll give it a go. So 21, it is 1650 north, 40 west. 1650 north, 40 degrees west. That's the first one. Second one is 1230 south, 60 west. 1230 south 60 west. 1230 south, 60 degrees west, south 60 west. Okay, so there it is. So do the same thing. So there's two tugboats this time. Pushing, pulling, I guess they push, don't they? Pushing on a ship in those directions. We want to know what's the result. Which way is that ship going to go? What's going to happen? So these are the kind of things, they need to calculate in real life to figure out how to do things. So how do you start? You start by drawing an axis system, right? And you put the ship right at the origin, just to make things as simple as possible. Put the ship right at the origin, and then draw those two arrows, the two vectors. So one's going north, 40 west. So here's north, south, east, and west. So north, 40 west. That was a little longer, so kind of maybe like that. So this is 40 off there, and then the purple one. Am I going to? I don't want to do it before you do it. So go ahead, do the purple one now. So that's north, but 40 west. So the other one is 1230 south, 60 west. So straight south, but then 60 west of that. So that'd be kind of like that. No, not so long. Kind of like that. And this is 60 like that, huh? We're good on those two. Now for both of those, find the direction angle. You can go negative or positive, it doesn't matter. Like if you want for the purple one, because this is 0, you got to go from 0 though. That's the crucial piece. Either way. So for to this one, I could go from 0 that way, it'd be negative if I do, that's fine. Or you could go from 0 that way. Whatever. So like if I go this way, how far would that be? Well, this amount is 90, and that's another 60. So that would be negative 150. That'll work fine. Or you could go from positive, and that'd be like 180 and 30, 210. Either way, it's the same angle. It's the same direction you're pointing. Negative 150 or positive 210. They're the same direction. Does that make sense?
And the one for the first one would be from 0 to the 40?
Yeah, they're always from 0. They're always from 0. It's just whether you go positive or negative, either one's fine. As long as you go from 0, either one's fine. So if I'm going from 0 to there, what's it going to be? 90 plus 40, huh? 130? That one's 130. We good on that? So you can go either way as long as you start at 0. That's what a direction angle means. From 0. From 0. So from 0 down. I just went down. That's 90. 90 and 60. 150. Everybody see how I got that 150? I just did 90 plus 60, but then made it negative. 90 plus 60. And then made it negative. It's negative 150. So we've got those two direction angles. So now go ahead and find the vectors, right? So you know the formula for the vectors. It's going to be 1650 cosine of, what is it, 130? So his direction angle is 130. Cosine of 130i. Plus 1650 sine of 130 J. Good, get the numbers there. So I'll do that too. Probably use like two places of accuracy, 2 decimal points. You want to use a couple places because in the end they want it accurate to like one place, don't they? So you better use 2 or 3. For now, I'll use 2, I guess. I got that one. And then the other one is going to be 1230 cosine. I'm going to use the negative 150. I plus 1230 sine of negative 150 J. So I'm getting negative 1065.21I minus, did you get a 615J just straight?
Yeah.
All right, so we got the two vectors now, right? We got the I and the J for both vectors. It's always good to double check for a second that you got your signs right, in case you got some angle way off. What I mean is, look at the red one. The red one is going left and up. So the I should be negative, yep, and the J should be positive. Right, it's looking good. Does that make sense? Left and up. Negative I, positive J, huh? How about the purple one? Purple one, the second one, should be left and down, right? That's left and down. So So should both be negative. Left and down. Yeah, it's looking good. Looks like probably I haven't messed up with some angle. It's just a good double check in case you accidentally get the wrong direction angle or something. It's looking good. So now just add those two together, get the resultant vector. And then you got to find the magnitude, which is the Pythagorean theorem, square root of a squared plus b squared, and the direction angle, which will be inverse tangent, but you got to adjust it for the quadrant. I'll show you. So let's do that. So I'm going to go to a fresh screen here. So the first one then is minus, so the first vector is minus 1060.60i plus 1263.97. 97j. The second vector is minus 1065.21i. 21i. And minus 615j. So the resultant vector, so you just I with I and j with j, huh? So what are you going to get there? 1060.60 plus 1065.21. I'm getting 2125.81 negative. And the other one, 1263.97 minus 615. I'm getting plus 648.97J. Okay, so we have the resultant. That good? And let's double check. That resultant is what? It's back and up, isn't it? Negative, positive. Back and up. That's the result of those two forces, back and up. Does that seem right? Yeah, that looks sort of right. The result seems to be kind of like right here, huh? Back and up. The result of an up left and a down left is back and up a little. The up is more than the down. So, yeah. So that's the net force pushing on the the two tugboats pushing will have that resultant direction and force on the other ship. So let's find now the magnitude of R. So what is the total force? You know how to do that, Pythagorean? Square root of negative 2125.81 squared plus 648.97 squared. I'm going to use I've already got it on the screen here. And I'm getting, so the magnitude, well, I'll just write over here, is 2222, bunch of twos, 0.66. Y'all get that? So that's the total force acting on that ship from the two tugboats, 2,222 pounds of force. Because they kind of, they add up sort of, but they sort of, some parts of them eliminate each other because one's going up, one's going down, huh? There's a little bit of canceling out, but a little bit of combining. Net result is that. Finally, they want the angle. Are we already caught up to there? Because the angle's going to be a little tricky. Well, the first part's normal. At first, it's just normal. Like, how do we find the angle? The resultant angle. Inverse tangent. Just go inverse tangent of J over I. You with me? So we always find the angle. This is the angle for the resultant. The resultant angle. When all is said and done, what direction is it going to go? It's inverse tangent of J over I. So that's inverse tangent. What's the J? That right there, 648.97 over the I. Oh, yeah. You know what? I forgot what I told you. Is everybody caught up here? Everybody able to track with me on this? Yeah, what we want to do, here's the trick. We see where the angle is actually going to be. It's in the second quadrant, isn't it? The actual place is the second quadrant. It's right there. So how do you get that? Well, there's different ways. I'm not sure exactly what Math Excel will tell you to do, but I found this is the easiest for the students over the years. Just do the inverse tangent of the positive. Positive I, but like, no, don't use that negative sign there. Why? Because that way I'll get a first quadrant answer. Everything's positive in the first one. Yeah, but your vector's not in the first quadrant, right? And then I'll adjust it for the quadrant I'm in. If you don't do that, what'll happen, because you might think, well, can't I just do it straight and it'll always work out? Just do it just like that? No, it won't. Because of the weird stuff with remember the inverse sine, cosine, tangent? Remember they have certain quadrants they go to and certain ones they don't? It's all real confusing. So here's what I think is the easiest thing to do. Just do inverse tangent for both positive. You guys tracking with me? This will become a major issue as we keep going. So you want to, the sooner you can get this down, the more it'll help you. It's not going away. It's going to come again and again and again and again, even in the next chapter. So it's finding a direction angle. So here's the game plan. I'll follow it every time. Inverse tangent of just the positive J and I. That way I'll get a first quadrant reference angle, and then I can easily find it because I know where it's actually at. It's actually in the second, you draw it, and it's actually in the second quadrant. So just do positive over positive, 2125.81. Hit the buttons on your calculator. I'm going to do that too. I'm getting 16.976 degrees, but that's the first quadrant. Remember, because I made everything positive, so that's like if the thing was right here. This is 16. So in other words, that's from the x-axis. So I'm probably not making a lot of sense. Let me do a better job on that. So in other words, let me draw this bigger. Our angle, remember, our resultant angle is actually headed up and left, isn't it? How do I know? This is left because it's negative, and this is up because it's positive, huh? It's up and left, right? It's left on I, negative on I, positive on J. So it's in the second quadrant. So when I get this 16.976 answer, that means that's this angle. That's the reference with reference to the x-axis, 16.976. So how do I find the actual angle from 0 degrees? That's the direction. That's the one they always want. What am I going to do? Now 180 minus it. We're in degrees, so we'll do 180, right? Because it's all the way to here, 180, back up the reference, huh? Does that make sense? The actual angle's in the second quadrant. So it's going to be 180 minus, remember whenever we find the second quadrant, so our angle is going to be 180 minus 16.976 degrees. So there it is. I'm getting 163.02. I don't know how far they want me to round. 163.02 degrees. That's the actual direction that those two tugboats are going to together combine to push that ship in. That's the result of their pushes. Let me double check. I want to make sure that's right. So what did we get there? That and the resultant was 16 point. Yeah. Questions I can answer on that. Is that making sense? Those are long, huh? All right, we good? I'm going to move ahead. Okay. So basically, right, they're saying some stuff over here. Let's ignore this. Let's just go down to here. That other stuff will make sense in a minute. Force 1 is 5a minus 5j. Yeah, let me just write it here. 22. So force 1 is 5a minus 5j. And force 2 is 4i plus 2j. I'm sorry, I forgot. 4i plus 2j. 4i plus 2j. Find the resultant force. Okay, so question A, what's the result of those two forces? What do we do to find the resultant force? What do we do? Oh, no, just add them up. So the results, just add them up. Just I with I, J with J. Yeah, if we want to find the magnitude of the result, that's when we do the, yeah, is that clear? Back over here. See, that was magnitude of the resultant. See the bars? That's when we do the Pythagorean. It's when you want to know how long is the r. Everybody getting the difference? There's the r vector. Yeah, let me, I know you guys are new to this whole world, so I've been doing it for like a long time, 20, 30 years. So I'm very used to it. So so there's a vector, and then there's the length of the vector. Those are different things, right? If you say a vector, you mean I and j. If you say the length of the vector, then you don't mean I and j. You just mean how long it is, like the resultant. You mean the magnitude, I should say, the magnitude of the resultant. That's different, right? If I say the resultant vector, that's I and j. If I say the magnitude of it, that's its length. That's the square root of a squared plus b squared. Okay, so they're saying they want the resultant force. That means they want a vector. So they want me to go I with I, 5 and 4, 9i, and j with j, minus 5j plus 2j, minus 3j. So there's the resultant vector. I just added up. That's just f1 plus f2. And, yeah.
Do they want you to reduce or factor out?
No. And then B, what additional force is required for the given force to be in equilibrium? So question B now, they're saying, what force required for equilibrium? Think about that for a second. Okay, so what do they mean by equilibrium? What do they mean by that?
Balance.
Yeah, balance. Yeah. So in other words, this resultant force is pushing 9 to the right and 3 down. Right? 9i minus 3j. Whoops. That's the resultant force. Does that make sense? It's right and down. It's 9 to the right, 3 down. 9i minus 3j. So it's down and to the right. That's the resultant force. So if you have an object, say you have something there, that is being pushed on down to the right, it's going to move down to the right unless it has another force going. Do you know any of Newton's laws? Equal and opposite. We need an equal and opposite force to keep it in equilibrium. So in other words, if you're pushing on something down and to the right, you need something pushing up and to the left to keep it in perfect equilibrium. So it won't move anywhere, right? Like why is this computer screen right here right now, why is it not moving? Well, because it's in equilibrium, which means there's forces acting on it right now. It weighs something, right? And its weight, gravity is pulling down on its weight right now. The earth is pulling down on this screen, pulling it down, wanting it to go down. Why doesn't it go down? Because what's pushing up on it? The desk is pushing back up on it. How much is it pushing up? I don't have to guess exactly how much it weighs. Otherwise, it would be moving, right? Its weight down is being exactly balanced by the table's push up. That's why you're not moving, right? Maybe you're moving a little. But if I'm standing here, my weight is gravity's pulling me down, and this ground is pushing back up on my feet with exactly my weight. Right? So that's why I'm not moving. It's forces in equilibrium. So anyway, long story short, I'm making this long story too long. So you just got to do the opposite. It's just going to be minus 9i plus 3j. Done. That's just opposite. That's all it is. I just did opposite of I, opposite of j. Done. That's the opposite force, which will keep it in equilibrium. It's opposite. It's because I'm doing physics with my daughter right now. I'm wanting to do a big old physics lecture. 23. So let's go. So basically they want you to get all those forces and add them up. Are there 4? Yeah, 4. There's 4 arrows there, huh?
So many fours.
Yeah, right. Yeah, there's a lot of 4s. They want you to get all those vectors. Basically, I'm gonna write ij for all those vectors and add them all up. That's what this problem is. So let's go one at a time. Force 1. Which one's 1? Is it this guy?
Yeah, I think so.
Yeah, okay. We'll call him force 1. It looks like force 1. So he's going back 4. Right?
Is he all the way at the 4 though?
I think. Oh, you're right. Thanks. He's like 3, huh? Now this is not a very good. What if I can? Here's what you can do to blow it up. So number 23. Yeah. So force 1 now is, good observation. It's back 3, huh? So force 1 then would be negative 3I. Doesn't have a J component at all. It doesn't go up or down at all, does it? It's just straight back 3. You with me? This is at negative 3 because it's halfway. See, those marks must each be 2's, right? This must be negative 2, negative 4, negative 6, negative 8. See how that's working? So it's halfway, so it's negative 3I. Good. Now what about force 2?
It's just a J.
No, it's back a little bit, isn't it? Yeah, it looks like it's back 1, up 3. Doesn't it look like this is 3? Because this goes by 2s. 2, 4, 6, 8, right? 6, 8. So that looks like it's back 1, up 3 to me. Is that what you think? So this looks like back 1, up 3. So it's back 1I, up 3J. Good. That's force 2, right? Back 1, up 3. What about force 3?
Down 8.
Yeah, force 3 is over 4, down 8. Over 4, down 8. So force 3 is 4I minus 8J. Is that good? So see how I'm doing this? And then finally, force 4 is just straight down, isn't it? Just down 3J. Straight down 3. No I component at all. Good? Then just add them up. I just want you to add those up. Add the I's with the I's, the J's with the J's. So the resultant force, let me do the I's here. Minus 3I, minus 1I is minus 4I. Plus 4I, that's 0I. It's funny. Okay. And then what about the J thing? 3J minus 8J is what? Minus 5. And minus 3 more is minus 8? Minus 8. Yeah, the easy way would just be to cancel the minus 3 and the plus 3, huh? It's minus 8J. So it's 0I minus 8J. So the result of all of those are 4 ropes tied to a point pulling in those directions. Then the result of all that is actually a straight down. Why is it? So they're saying the result of all those arrows is a straight down 8. Why? What about all the sideways stuff? Cancel each other out, yeah. The amount this one pulls to the right, 4, is canceled by the amount these guys are pulling left. So it's actually a straight down pull of 8J. And then they ask the question, okay, so what equal opposite force is needed to keep, if this is something you want to keep from moving, keep it in balance, what would be the opposite force?
0I.
Yeah, it's just going to be plus 8J, or 0I if they want, yeah. 0I plus 8J. Good enough? Doing a little physics here. All right, I'm going to move on one more. Okay, so number 24. Plane speed is 175 miles per hour. So what we're doing on this problem is we're talking about a plane and then the wind and how those things affect. So this is how people would calculate the effect of wind on a plane and what that does for direction and all that kind of stuff. So the V is the velocity for the plane. So this vector right here is the plane. See that arrow? That's the plane's velocity. That's how the engines and the nose of the plane are aiming and pushing that plane. It's going 107. The engines are roaring to move it at 175 miles per hour in that direction. But the wind is playing a part also. The wind is blowing straight east at 41 miles an hour. So what's going to be the result? What's going to be the overall effect of both the engine and the engine's heading and the wind together. Where's that plane really going to head? They're actually showing it right on the diagram. I haven't talked much about this, but you can actually add two arrows end to end. Meaning, if you have like a plane vector that's going off, say, that direction, and a wind vector that's going like that, and you want to know the result of the two of them, you can just take that second, here, let me make it a different color, that wind vector, this is the wind and this is the plane, you can take that wind vector, and remember, vectors can be moved. Remember me saying that it didn't matter where they sit. Remember I did what's it called, Despicable Me? Is that the movie? Right, I am vector, I am magnitude and direction. That's right, he's got that mathematically right. Vector is just magnitude and direction. How much? Where, but not position. So I can move this wind vector wherever I feel like moving it. As long as it's straight to the right that far, it's the same vector, right? Specifically then, most usefully, I could put it at the end of the plane vector. And then that would tell, that's how they visually add vectors. That would visually show you the plane vector plus the wind vector will end up having a result from there to there. That's how you find the result. You just add them end to end like that. And you could do it either order. You could do the wind one first and then take the plane one and move the purple one to the end of the plane, and guess what it'll do? Same result. It's going to go from here to here, however you do it. So spatially, visually, that's how you see the effect of two vectors and how they'll add to each other. The resultant force is going to go up to the right, but not as up as the plane was aiming. Anyway, so now let's go back and do the math. That's just spatially. They're not really asking me to do that. I'm just explaining what they're doing on that diagram. This is the resultant vector. See how they took the V and they put it down here? And they're showing the result. Anyway, you don't have to do anything with that. I don't think, let's see all that's required here. So let's do that. Let's write the first vector. Let's write the V, the plane's engine vectors. So how are we going to do that? Well, you know how to do it. It's always, cosine theta I plus sine theta j. But you got to have the direction angle when you use that formula. Is 43 degrees the direction angle? No, it's got to be from 0 to there, huh? So it's 90 minus 90 degrees minus 43. What's that, 47? So 47 is actually the direction angle from 0. So it's going to be what? 175 miles an hour. So 175 cosine 47I plus 175 sine 47J. That's going to be the plane's engine vector. That's the V they're calling it. And then what's going to be the wind vector? Let's write that over here. What's the wind vector?
41 cosine 0.
It's straight to the right, isn't it? Yeah. So I'm just going to go 41I. Done. It's got no J to it at all. Right? The wind vector is straight to the right. 41I. No J component at all. So you don't even have to do the official. But you're right. But what John was saying is right. You could do cosine of 0. Yeah, if you wanted to be formal, you couldn't we do the because 0 degrees, right? The wind vector is at 0 degrees straight, isn't it? Yeah, if you did, guess what you would get? If you did 41 cosine 0I plus 41 sine 0j, sine of 0 is 0, that whole part would drop out. Cosine of 0 is 1, you would get the same thing. It's the same either way. All right, does that make sense for those two vectors? Compute them and do all that we normally do. So let's do it. Let's do it kind of quick. We don't have forever on this stuff. My goodness, these are long. So the first one, 175. Oops. So I'm still doing. So the plane vector, 175 cosine 47I plus 175. Oops, sine 47J. So let's find that. 175 cosine 47 I'm getting 119.35 plus, and then 175 sine 47. I'm getting 127.98 or 99 J. So I'm getting the plane vector like that, and then the wind vector. That one, what was that? Yeah, 41I, huh? So the wind vector, 41I. So then put those together, get the resultant vector. And so that would be (160.35I). What's up? Just add them up there? Yeah, and the J's just stays the same. Is that good for the resultant? And then they want the magnitude of it, like usual. So the magnitude of it, the length of it, that's the Pythagorean. The square root of the 160.35 squared plus 127.99 squared. And I'm getting 205.17. And then they want the angle of it. So that's going to be inverse tangent. Remember what we do? Positive J over positive I. What's nice is they already are both positive. So it is just going to be first quadrant. So it's going to be inverse tangent of the J over the I. All right, let's find out what that is. (38.596 degrees), like that. All right. Now, but remember, you have to figure out where that's actually at. Where is that? That resultant force is right and up. So it's like that. The resultant force. So that because that angle you get is always going to be a reference angle, isn't it? So whenever you do tangent inverse, making both of those positive, you're getting first quadrant from the x-axis. So that means this angle here is 38.6 degrees right there. Okay? So, and here's what they want me to say. They want me to give that as a heading. How do you give that as a heading? Now, when you give a heading, let's look back to the answers. Oops, I never did it, huh? All right, I'm going to have to go out of physics. So is that good? Questions on that? So we got north 51.4 degrees east on that last one because when I did inverse tangent, I got 38.596, and that was from the x-axis. When you give a bearing, you give it from north. So I had to go from north. I had to go 90 minus it and got that answer.